Alright guys, this is going to be a foreseeably long video. We're going to go ahead and try and prove all the important properties of limits. So let's go ahead and take a look at some of the properties we're going to try and prove. So this is given that the limit as x approaches c of f of x is equal to L, and that the limit as x approaches c of g of x is equal to k. So we know that these two limits exist. We know that the limit, that this limit right here as x approaches c of f of x is L, and this limit is k. So given those two things, this is what we're going to try and prove. First, that the limit as x goes to c of k times f of x is equal to k times the limit as x goes to c of f of x, which is equal to KL. And this is going to be when k is some constant value. It doesn't depend on x, which is our variable. Second is going to be the sum indifference rule. So this is the limit as x goes to c of f of x plus or minus g of x is going to equal the limit as x goes to c of f of x plus or minus the limit as x goes to c of g of x, or is equal to L plus or minus k. And of course the plus or minus is going to correspond just how you would expect. If you have a plus here, you're going to have a plus here and a plus here. If you have a minus, you're going to have a minus and a minus. Third property, this is our product property. The limit as x goes to c of f of x times g of x is equal to the limit as x goes to c of f of x times the limit as x goes to c of g of x is equal to L times k. Fourth is that the limit as x goes to c of f of x over g of x is equal to the limit as x goes to c of f of x over the limit as x goes to c of g of x. And this is going to equal L over k, but obviously provided that k cannot equal 0, because we know we can't divide by 0. So this property is only true when k does not equal 0. And 5 is going to be our power property. Limit as x goes to c of f of x to the n is going to equal the limit as x goes to c in parentheses of f of x right here to the n, which is going to end up equaling L to the n. So these are the 5 properties we're going to set out to prove in this video, and let's get to it. Alright guys, we're going to start looking at our first property, and we're going to call this the constant property. So this is a very important property. It seems pretty basic. It is important to prove, and something we do in this proof is going to be really important for future proofs we're going to do, especially in this properties video. So what we're trying to prove is that given that the limit as x goes to c of f of x is equal to L, so this is our given, we want to prove that the limit as x goes to c of k times f of x is equal to k times the limit as x approaches c of f of x, which is going to equal KL. So if you take a look at what that would mean, is that essentially that we can pull constants in and out of limits. So let's go ahead and start our proof. We're going to go ahead and write down our given and go from there. So we know that the limit as x goes to c of f of x is equal to L. So what does this tell us? Well, we're going to use our epsilon delta definition. We know that for any epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon over the absolute value of k, or constant k. So that constant is just any real number. And this is probably the point where you're a bit confused, or something, you're seeing something you haven't seen yet, where you're wondering, why isn't this just epsilon? Why can I say this statement and have it still be true? If you guys remember from the definition of a limit, we said for any epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus l is less than epsilon. So why can I say that this is epsilon over the absolute value of k? Well, to understand why I can do that, we need to really talk about what a limit is again. And if you have an involved understanding of what a limit really means, you'll see why this statement that I've written right here is still true. So let's go over that. And this is going to be pretty important because we're going to do stuff like this in other proofs. So what the limit tells me is that because as x is getting closer and closer to c, f of x continues to get closer and closer to L. If I'm to pick a range of values around L, and this is a number line of f of x values. So these are f of x values. And if I'm to pick a range of f of x values around L, from L to some point here, and I'm not defining that point yet, and this is some distance, we know this is some distance, I'm going to go equal distance this way. So if I'm to pick an interval defined by these two distances, so this is a range of f of x values right here. So this is letting me know my range of f of x values. And I have the ability to make this distance whatever I want it to be, any real number. And I make that range that I will be able to find a corresponding range of x values around c, except possibly at c, and this is from c minus delta to c plus delta. I can find that corresponding range of x values such that when I pick those x values from here and from here, I will get back f of x values inside this range right here. So I can make this range of f of x values as big or as small as I want, and I will always find a delta. In the past, we have made the decision to make this range the size of epsilon. And we've said for any epsilon, there exists a delta. Why? Because for any range, there exists a delta. That is correct. So if we made our range defined by the size of epsilon, we would indeed find a delta. What we're saying now is that our range is defined by epsilon over the absolute value of k, where k is some constant. So all we're doing is we're making this a different range defined by the distance is now defined by epsilon over the absolute value of k. And we know, because the limit exists, regardless of what value of epsilon over the absolute value of k we use, which is essentially the distance of the range, regardless how big we make this interval or how small we make the interval, we will always find a delta. So that means for any epsilon over the absolute value of k, there is a delta. Well, if we wanted to find the corresponding delta for just the epsilon value, all we have to do is multiply this term by the absolute value of k. So for example, if I was to make this range right here confined to L minus 0.1 all the way to L plus 0.1, and I got back a delta value of some number, so I'm getting back a delta value, I know that delta value exists. To find what epsilon value that delta value corresponds to, I just have to multiply 0.1, which is epsilon over the absolute value of k, by k. So for any epsilon greater than 0, I know that delta still exists, because I know it exists for this epsilon over the absolute value of k. I know it exists for that specific range of L values. I know there's a delta. So I just have to take this value, multiply it by the absolute value of k, and I found the epsilon that that delta value corresponds to. So I know this statement is true, that for any epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus l is less than epsilon over the absolute value of k. And since I can make this value right here any positive number, epsilon over the absolute value of k, I can make that any positive number. I can also find any epsilon that I want that is a positive number. So that's how I know this statement's true, and that's really important to know that I can do that in these proofs, because now this proof becomes pretty easy. All I do is I'm going to modify this statement by multiplying both sides by the absolute value of k. So now I'm going to rewrite it, and I get for any epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus c, which is less than delta, then absolute value of k times the absolute value of f of x minus L is going to be epsilon. Well, it's just going to be epsilon because we're multiplying both sides by the absolute value of k. And we know by the property of absolute values, when we multiply two absolute values together, we can rewrite this as k, we can just distribute it through k f of x minus kl is going to be less than epsilon. So for any epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than x minus c is less than delta, then the absolute value of k times f of x minus k times l is going to be less than epsilon. And by the epsilon delta definition, that lets us know that the limit as x approaches c of k times f of x is equal to k times l. And of course, this is also the same as k times the limit as x approaches c of f of x. And that's our constant property, that we can pull that k in and out. And k can be any value you want. It's any real number. Well, except 0. K can't be 0 because right here in our proof we're dividing by the absolute value of k. So we can't divide by 0, so it becomes invalid in that case. But for any time that k is not 0, and of course when k is 0, k times f of x will just become 0. And we show later that the limit of a constant is just the constant itself. That's a later proof that uses the epsilon delta definition. But for all the other k's that are not 0, any real number, we can just pull that k outside of the limit, and that's how you prove that. The next property we're going to look at is the sum and difference property. So let's look at the sum property first, and that is the limit as x goes to c of f of x plus g of x. This whole thing is equal to L plus k. And remember that this is when the limit as x goes to c of f of x is L, and the limit as x goes to c of g of x is k. So to do this proof, we're going to need to prove a little inequality, and that inequality is that if a and b are any two real numbers, negative or positive, that the absolute value of a plus the absolute value of b is greater than or equal to the absolute value of a plus b. So this, I believe, is known as the triangle inequality, and to prove it, we're just going to look at the 4 instances where we can really look at it and where it can occur, and that's going to be when a is greater than 0 and b is greater than 0, when a is greater than 0 but b is less than 0, when b is less than 0 and a is less than 0. Let me flip that just so I can keep all the a's in the same column. So there's going to be an a is less than 0 and b is less than 0. And the fourth case is going to be when a is greater than 0 and b is going to be, fourth case is when a is less than 0 and b is going to be greater than 0. So let's look at our first case. When a is greater than 0 and b is greater than 0, a plus b is always going to be greater than 0. So the absolute value of a plus b will just be a plus b. And a, the absolute value of a will be just a, and the absolute value of b will be just b. So we get a plus b equals a plus b. So we can see in this case the equation holds as we have this less than or equal to sign right here, so we're using that equal to portion. So the equation holds in this first scenario, so we're going to put a check right here. We're going to look at when a is greater than 0 and b is less than 0. So there's actually 2 cases where this splits up into, and this is when the absolute value of a, or the magnitude of a, is going to be bigger than the absolute value of b, and when the absolute value of a is going to be less than the absolute value of b. So taking a look at this, when the absolute value of a is bigger than b, a plus b will still be positive. So we're going to get a plus b, we're just going to remove that absolute value, is going to be less than or equal to a, and the absolute value of b when b is negative is going to be minus b. But because b is negative, when we're doing minus b, this is actually going to be a number over here that's greater than a, because we're doing minus and negative, and when we add a plus b over here, this is going to be a number that's less than a, because b is less than 0. So we can say that this still holds true, because in this scenario, a minus b is actually greater than a plus b. Now we look at the next case, when the absolute value of a is less than the absolute value of b. In that case, then a plus b will be a negative number. So when we get rid of this absolute value, the absolute value of a plus b is actually negative a minus b, and we're going to say that that is going to be less than or equal to the absolute value of a, which is just a, and the absolute value of b, which in this case is minus b. So this still holds true, because this is most definitely going to be a, well, if you look at this, a is positive, so we get negative a, and we get minus b. So we're actually essentially adding the magnitude of b. And in this case, a is bigger than b. Or sorry, b is bigger than a. So this will end up being some positive number. And we're saying that number is going to be less than a minus b, in the case where b is less than 0. So this is going to be bigger than a. So this number right here is bigger than a. And this number right here is negative a plus b. Well, how can we show that this is true? Well, we can simplify this right here and add b on both sides, and it becomes negative a is less than or equal to a. Well, we know for a fact that negative a is less than a, and that reason being is because a is greater than 0. So for example, if a was 3, negative a is obviously less than a, negative 3 is less than 3. So now that we've shown that, we're going to look at the case where a and b are both less than 0. When a and b are both less than 0, a plus b will definitely be negative. So when we say the absolute value of a plus b, what we really mean is minus a minus b. And we want to see, is this less than or equal to the absolute value of a plus b? Well, the absolute value of a when a is negative will be negative a, and the absolute value of b will be negative b. So obviously these two things are equal, so our inequality still holds. And now we can split this into two cases again, when the absolute value of a is going to be greater than the absolute value of b, and the absolute value of a is going to be less than the absolute value of b. And when we look at this, a is less than 0, b is greater than 0. So when the absolute value of a is greater than the absolute value of b, this will be a negative term. A plus b will be a negative term. So when we take away that absolute value, we get negative a minus b is going to be less than or equal to, and the absolute value of a will be negative a. The absolute value of b, because b is greater than 0, will just be b plus b. So how can we show this to be true? We'll add a on both sides of the inequality, and you get negative b is less than or equal to b. Well, we know negative b is indeed less than b. Why? Because b is always a positive number in the case we're looking at right now. So again, it holds, this inequality holds for when a is less than 0 and b is greater than 0, and the absolute value of a is greater than b. Now we have to show for the absolute value of a less than b. Well, in that case, a plus b will be a positive number, and the absolute value of a plus b will just be a plus b. And we're going to say, is this less than or equal to the absolute value of a, which is going to be negative a, and the absolute value of b, which is just going to be b. Well, a is less than 0, so when we do negative a plus b, we're really getting back a number that is bigger than b. And this number right here is going to be smaller than b. Why? Because a is negative. When you add a negative to b, you get a number smaller than b. So we can say that we know that the negative a plus b is greater than a plus b. So we've shown for each instance when a and b are any positive or negative number that this inequality is true right here. And this is going to be very important. So let me erase all this to make room for our limit proof. And I'm just going to write this inequality to the side. And this is something we know to be true. and we're going to use this in our proof. So let's start out with our proof for this statement right here. So we know based on this limit that for any epsilon greater than 0, there exists a delta 1 greater than 0 such that if, let me make some more room, if 0 is less than the absolute value of x minus c is less than delta 1, then the absolute value of f of x minus L, and I'm going to say it's going to be less than epsilon over 2. Why is this true? Shouldn't these both just be epsilon? Well, if you remember what the limit means, it means that for any amount we confine f of x around L, and this defines the size of that interval around L where f of x can lie in, we can find that delta. So why does that mean for any epsilon there's a delta? Shouldn't it mean for any epsilon over 2 there's a delta? Well, we know that if there's a delta for epsilon over 2, there is a delta for epsilon as well. All we have to do is multiply our epsilon over 2 by 2, and we know that any epsilon will also have a corresponding delta. So we know that this statement right here is true. What the limit means is that for any range we confine our f of x values around L, we will find a corresponding range to confine our x values around C, except at C, which is why we have this greater than 0 here. So we know this is true. We also know that for any epsilon greater than 0, there exists a delta 2 greater than 0 such that if 0 is less than the absolute value of x minus c is less than delta 2, then the absolute value of g of x minus k is going to be less than epsilon over 2. Now, again, we can find any epsilon value. We can make this epsilon value anything we want. So we can make it the same for both of these, but there's no guarantee that our two deltas are going to be the same. We just know that there are two deltas, one for each, that do exist. And the reason is because we know that these limits exist, and this limit equals L, and this one equals K. So now if you look at this, what this is saying, here we have a number line of x values around C with a distance of essentially delta 1. This should be a minus sign. Let me erase that. And any x values inside here or inside here, when we plug them in, we get back f of x values that are inside a range around L defined by epsilon over 2. And similarly, over here, we have c, we have x, and now we have c plus delta 2 and c minus delta 2. And we take any x values from here, we get g of x values minus k that are less than, where the distance between the g of x values and k is less than epsilon over 2. Well, I'm going to do this step, and we've done this before, where I'm going to say delta is equal to the minimum, the smaller of delta 1 and delta 2. Why do I do that? Because when I pick the smaller of the two, I find an interval where both these statements are true when I choose x values from that interval. And the reason being is because in this case I've specifically drawn delta 2 smaller than delta 1. Do I know that's true? No, but I'm just using it for example, where if I take anything from inside delta 2, not only will it make the absolute value of g of x minus k less than epsilon over 2, it will also make the absolute value of f of x minus L less than epsilon over 2. Why? Because all the values inside that smaller interval are also in that bigger interval. So that's how we kind of relate these two. So knowing that, where delta is the minimum of those two values, we can rewrite our epsilon delta statement saying for any epsilon there exists a singular delta such that if 0 is less than the absolute value of x minus c is less than delta, and we're just using our delta, which is the minimum of the two values, then this inequality, the absolute value of f of x minus L, will be less than epsilon over 2, and in that same region, the absolute value of g of x minus k will also be less than epsilon over 2. And this is of course when delta is the minimum. We're going to say delta is the minimum of delta 1 and delta 2. So now, knowing this, we're going to go ahead and do some algebra and see what comes out. Based on this statement right here, these two inequalities, we know that the absolute value of f of x minus L plus the absolute value of g of x minus k is going to be less than epsilon. Why do we know that? Because this statement, this value right here is less than epsilon over 2, and this one is less than epsilon over 2. So the sum of the two together is going to be less than epsilon. That's just some algebra. And now, this is where we're going to use our triangle inequality. We're going to treat f of x minus L as A and g of x minus k as B. So what does that let us know? That lets us know that, now let me write it like this. I'll write this over here, f of x minus L plus g of x minus k, should be a minus sign, minus k is going to be less than, or greater than or equal to a plus b. So f of x minus L plus g of x minus k. And we can go ahead and rewrite this right here if we just rearrange our terms as f of x plus g of x minus, in parentheses, k plus L. So we know that this is greater than this, that the absolute value of f of x minus L plus the absolute value of g of x minus k is greater than the absolute value of f of x plus g of x minus, in parentheses, the quantity k plus L. Now, we also know that epsilon is greater than this right here. So that lets us know that we can actually say that epsilon is not just greater than or equal to, but epsilon is going to be greater than the absolute value of f of x plus g of x minus the quantity k plus L. So for any epsilon greater than 0, we know that there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x plus g of x minus the quantity k plus L is less than epsilon. And by the definition of a limit, this states that the limit as x approaches c of the function f of x plus g of x is equal to k plus L. And that's how we prove our sum property. From there, how can we prove our difference property? Well, it turns out to be quite easy. We don't need to know any of this anymore. Now that we know that this property right here is true, all we have to do is recognize, based on our last property, the constant property, that the limit as x goes to c of k g of x is equal to k, in this case, little k times k, where k is some constant. That means that the limit as x goes to c of f of x plus k g of x, based on our sum property, is just f of x plus, not f of x, it's L plus little k, our constant value, it can be any constant, times k. Well, let k equals negative 1, because this is true for any k, any constant that's a real number. And then we get the limit as x goes to c of f of x minus g of x, and we see how that is equal to L minus k. So the next property we're going to look at is our product property. And this is that the limit as x goes to c of f of x times g of x is equal to Lk. And this is when the limit as x goes to c of f of x is equal to L, and the limit as x goes to c of g of x is equal to k. And this proof is kind of roundabout. It's not going to seem obvious what we're doing at first, but if you just follow through, you'll see how it proves this property right here. The first thing we need to do is show that the limit as x approaches c of f of x minus L is equal to 0. And we can use our difference property to show that. We know that this, well, let's go step by step. So this limit right here is equal to the limit as x approaches c of f of x minus the limit as x approaches c of L. that's x approaches c of L. And this limit right here is equal to L, as we defined up here. And this is the limit as x approaches c of some constant, that constant being L. And we haven't actually gone over this yet, but I'm going to go ahead and tell you that the limit of some constant is always the constant itself, so we get minus L. That's something we're going to prove in our next video on simple limits. We're going to go over that with the epsilon delta definition, show why that is true. But we've just shown that this limit right here is then equal to 0. And with a similar method, we can show that the limit as x approaches c of g of x minus k, which is going to be equal to the limit as x approaches c of g of x minus the limit as x approaches c of k is equal to k minus k, and that's also going to be equal to 0. So that lets us know that for any epsilon greater than 0, there exists a delta 1 and a delta 2 greater than 0, such that if let's erase that, 0 is less than the absolute value of x minus c is less than delta 1, then the absolute value of f of x minus L minus 0 is going to be less than the square root of epsilon. And let's take a look at that statement right now. All we're saying is we know this limit is equal to 0. So this is our function right here, which is why it's right here. We're subtracting what that f of x minus L value is approaching, which is 0. And we've gone over why I can put square root of epsilon. Remember, the limit says that I can confine this f of x minus L value around 0. I can confine the values of f of x minus L around 0, and I'll always find a delta to confine my x values around c, such that those x values give me those f of x values minus L values, f of x minus L values, around 0. And so why can I say for any epsilon there exists a delta? Well, if for any square root of epsilon that delta exists, which we know by the limit, then all I have to do is take that square root of epsilon and square it, and I have for any epsilon there still exists that same delta. So we know that that's true for delta 1, and now we're going to make the same statement for delta 2, and of course we're going to use our other limit, g of x minus k, then the absolute value of, this is going to be the absolute value of g of x minus k minus 0, and that is going to be less than the square root of epsilon. So now we have our two statements, but I'm going to do something, this is also something we've been doing quite a bit, and change this into a singular delta, which is going to equal the minimum value of delta 1 and delta 2, which is still going to be greater than 0, such that if the absolute value of x minus c is greater than 0 and less than this singular delta, then both these statements here hold true. And why is that? Why can we do that? Well, essentially, that picking that minimum delta is using our smaller of the two intervals. And the smaller of the two intervals of x values falls inside that bigger of the two intervals. So all these x values make both these statements true. And we've gone over that before with number lines, so if you need to review that, please do. So we know that in this interval of x values, the absolute value of f of x minus L minus 0, and I've gotten rid of a parentheses here, that should be there, is going to be less than the square root of epsilon, and the absolute value of g of x minus k minus 0 is also going to be less than the square root of epsilon. Well, one thing I'm going to show right here, and this is just a basic understanding of absolute values, is that the absolute value of f of x minus k right here times the absolute value of g of x minus k, and this should be a minus L. Sorry about that. When you have two absolute values being multiplied together, we can just write it together as one absolute value, so we get f of x minus L and times g of x minus k. And if we subtract 0 from this right here, of course it's going to be the same thing, so I'm just going to write this like that. So we know that the absolute value of f of x minus L times the absolute value of g of x minus k is equal to this singular absolute value right here. Well, based on our statements, we know that if we pick an x value in this delta range, then the absolute value of f of x minus L minus 0 is less than epsilon. And the absolute value of g of x minus k minus 0, and these minus zeros, we can get rid of those, of course. Subtracting 0 from f of x minus L doesn't make a difference, or the same for g of x minus k. So we know these two absolute values are less than epsilon. So when we multiply them together, like this, their product is going to be less than the product of epsilon squared, or epsilon, the square root of epsilon and the square root of epsilon. So their product is going to be less than epsilon. So look at what this tells us. This means that for any epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus c is less than delta, then the absolute value of the product of the quantity f of x minus L and the quantity g of x minus k minus 0 is less than epsilon. And if you look at this as based on the definition of a limit, this is what lets us know that the limit as x approaches c of f of x minus L, so this whole thing right here, times g of x minus k is equal to 0. Well, why in the world did we want to do that? I'll show you in just a second. So we're going to get rid of this right here. We know these two things to be true because we're going to need this space. And I'm going to rewrite this limit that we just proved, the limit as x goes to c of that quantity f of x minus L times the quantity g of x minus k. And this we know is equal to 0. That's what we just showed. And now we're just going to go ahead and do a bit of algebra. We're going to find out what f of x minus L times g of x minus k is. And this is just foiling. So we're going to get f of x times g of x minus k f of x minus L g of x plus lk. And we can solve this equation right here for f of x times g of x. So we get f of x times g of x is equal to, it's going to be equal to lk not lk, it's going to be equal to, let's write this again, f of x minus L times g of x minus k, that plus k times L plus, or k times f of x plus L times g of x minus L times k. And now, based on the fact that these two functions of x are the same thing, they're the exact same thing, we know that the limit as x goes to c of both of them is also going to be equal. So we're going to take the limit as x goes to c of both sides. And based on our sum slash difference product, we know that the limit of all these sums and differences is just going to be their separate limits added together or subtracted. So it's going to be the limit as x approaches c of f of x minus L times g of x minus k plus the limit as x goes to c of k f of x plus the limit as x goes to c of L g of x minus the limit as x goes to c of L times k. Well, we showed that this limit right here is equal to 0. If we pull out this constant, like we showed with our constant property, we get k times the limit as x goes to c of f of x, which is just L. And right here, we get the limit as x goes to c of g of x times our constant L, so we get plus L times k, and this is the limit of a constant, which we discussed is just that constant itself. So this limit becomes minus L times k. And then this over here, we have the limit as x goes to c of f of x times g of x. And look at what this simplifies to. If we just cross out this, and we add 0, we get finally that the limit as x goes to c of f of x times g of x is equal to LK. And that is our product property. That's what we set out to prove. So that's how you prove that the limit as x goes to c of f of x times g of x equals LK, given that the limit as x goes to c of f of x is equal to L, and the limit as x goes to c of g of x is equal to K. Okay, so this next property we're going to look at is the quotient property. And that is the limit as x goes to c of f of x over g of x is equal to L over K. And that is, provided that the limit as x goes to c of f of x is equal to L, the limit as x goes to c of g of x is equal to K, and K does not equal 0. We know we can't divide by 0, that's undefined. So how can we go about proving this? Well, what we're actually going to do is apply the product property, and we're going to split this up, make it look something like this. F of x times 1 over g of x is equal to L over K. And based on this, if you look at the product property, what you see is that if we're able to prove that the limit as x goes to c of 1 over g of x is equal to 1 over K, then we've effectively proved our quotient property. So that's exactly what we're going to go set out to do. And it is much more complicated than you might think. It's pretty roundabout. It is pretty confusing, but it is mathematically rigorous. So if you stick with me through this proof, it should hopefully make sense. So what we're saying is we know that the limit as x goes to c of g of x is equal to K. And what we want to prove is that the limit as x goes to c of 1 over g of x is equal to 1 over K. And so based on this limit, we know that there is a delta 1 greater than 0 such that if 0 is less than the absolute value of x minus c is less than delta 1, then the absolute value of g of x minus k is going to be less than the absolute value of k over 2. And this is where you might get first confused, and you might wonder, where's the epsilon in this proof? Well, if you've noticed, we've picked a specific value right here in this spot. It's not like epsilon where it's varying. And if you think about what the limit tells us, it lets us know that if we are to pick an interval of g of x values around k, we will always be able to find a corresponding interval of x values around c, such that when we pick x values from that interval, we will get back g of x values in that interval around k. So if we make that interval around k of size from g of x minus, from k minus the absolute value of k over 2 to k plus the absolute value of k over 2, essentially an interval of size dependent on the absolute value of k over 2, if we make that interval of g of x values, we will always be able to find that corresponding interval of x values, and that's what lets us know that this delta 1 greater than 0 does exist. So we know this delta value exists. And now we're going to go ahead and we're going to do some algebra, and we're just going to say if we have the absolute value of k, we know that this is equal to the absolute value of k minus g of x plus g of x. So that's just adding 0. It makes no difference. And now we're going to apply our triangle inequality. We talked about this inequality in the sum and difference video, and we know that this is going to be less than or equal to the absolute value of k, not a plus. It's going to be k minus g of x plus the absolute value of g of x. That's with the triangle inequality. We know we can multiply whatever's on the inside of an absolute value by -1, and it'll be the same thing. So I'm just going to do that here. I'm going to write this as g of x minus k. And now what I'm going to go ahead and do is apply what we just talked about here. Knowing that if I'm in this delta 1 range of x values, I know for a fact that the absolute value of k over 2 is going to be greater than the absolute value of g of x minus k. And that lets me know that this expression right here will be less than k k over 2 plus the absolute value of g of x. And this should be an absolute value of k over 2. So let's look at the expression I have now. When I'm picking x values inside this interval, I know that the absolute value of k is going to be less than the absolute value of k over 2 plus g of x, or that g of x is going to be less than the absolute value of k over 2. Just subtract the absolute value of k over 2 from each side, and now I'm going to essentially flip this inequality and flip my fractions. So I'm saying if this is a smaller number than g of x, then the reciprocal of this, 2 over k, the absolute value of k, will be a bigger number than 1 over, and this should be an absolute value here. I forgot it from right here. This reciprocal will be bigger than 1 over the absolute value of g of x. So that's what we need to know, and I'm going to take that and I'm going to keep that here because that's going to be important later on. So we know when we pick x values in that range that 2 over k is going to be bigger than 1 over the absolute value of g of x. And this is absolute value. Again, 2 over the absolute value of k is going to be greater than 1 over the absolute value of g of x. And now, based on this limit, we're going to go into another epsilon delta sort of discussion. Now we're bringing in the epsilon. For any epsilon greater than 0, there exists a delta greater than 0 such that, and we're going to call this delta 2, let's get this eraser out of the way, such that if 0 is less than x minus c, the absolute value is less than delta 2, then the absolute value of g of x minus k is going to be less than the absolute value of k squared over 2. And again, we don't really need this absolute value because k squared is definitely always going to be positive, but we're just putting it there for when we do some math with it later. It comes out nicer. And this is k squared over 2 times epsilon. So this lets us know for any epsilon greater than 0, we can find a delta sub 2 greater than 0, such that if 0 is less than x minus c is less than delta sub 2, then the absolute value of g of x minus k is going to be less than k squared over 2 times epsilon. And why does this make sense? It's the same reason. We can confine g of x around k in some interval defined by the size of this expression right here. And when we do that, we'll be able to find a corresponding interval of x values around c. How do we get the epsilon? Why is it true for any epsilon? Well, for any confinement that we pick, there's that delta value. All we have to do is multiply the size of that confinement by 2 over the absolute value of k squared, and we have an epsilon value. So we know for any epsilon value, that delta value does exist. And now we're going to do something we've been doing a lot before, and we're going to say that delta is equal to the minimum of delta 1 and delta 2, so the smaller of the two. And this will give us the smaller of the two intervals. And essentially, the smaller interval will be housed inside that bigger interval. So when we pick x values inside the interval defined by this new delta, not only will the statements of that smaller interval hold true, so not only will this inequality hold to be true, but this one will as well, because that smaller interval where one of the inequalities holds true is going to be inside the bigger interval, and in that bigger interval, that second inequality also holds true. So when we pick this delta, both those inequalities are going to be true. So we can write this now as delta instead of delta sub 1, and then the absolute value of g of x minus k will be less than k, the absolute value of k over 2. And along with that, also, I should write it now before I erase it, the absolute value of g of x minus k will also be less than the absolute value of k squared over 2 times epsilon. And we're going to go ahead and do a little bit more algebra. So we're going to start off, and this is almost on an unrelated note, but you can kind of see where this is going to go a little bit. 1 over g of x minus 1 over L should be something we're expecting, or 1 over k, sorry, because we're trying to prove that the limit as x goes to c of 1 over g of x is equal to 1 over k. And just giving this fraction right here, or giving these two fractions a common denominator, we can simplify this out to L, or sorry, again, it's k, minus g of x over, this is in absolute values, over k times g of x. And then what we can do is we can pull this out. Remember, the absolute value of two things multiplied together is just the absolute value of them multiplied together. If that makes any sense, we can split this up. What I'm trying to say is something like this. We can pull this out. This is a property of absolute values, that these two things are going to be equal. And that is very important. And then we can further actually split this up into 1 over k times 1 over g of x. So again, this right here is just all algebra. And now what we're going to do is say when we pick x values inside this interval defined by delta, we know that this is going to be less than 1 over the absolute value of k times 2 over the absolute value of k times the absolute value of k minus g of x. And we can rewrite k minus g of x. We can just multiply whatever's on the inside of this absolute value by -1. So we can rewrite this as g of x minus k. And where did this less than come from? Well, we know on this interval that k over 2, or 2 over k, is always bigger than 1 over the absolute value of g of x. So 2 over the absolute value of k is bigger than 1 over the absolute value of g of x. So we just said that if we plug in 2 over k instead of 1 over the absolute value of g of x, this expression will be bigger than this expression. So it comes from this inequality right here. And now we're going to use our second inequality from right here and say that on this interval, well, the absolute value of k squared over 2 times epsilon is bigger than the absolute value of g of x minus k on this interval defined by delta. So we can say that this is going to be less than 1 over k, the absolute value, times 2 over the absolute value of k, times the absolute value of k squared over 2 times epsilon. And when we simplify this expression right here, we can say these k's cancel and these 2 cancels, and we get epsilon. So we get that epsilon is greater than the absolute value of 1 over g of x minus 1 over k. So what did we just show? We showed that, and this should be a delta. Remember, we replaced it over here. I just forgot to erase that there. For any epsilon, essentially, for any epsilon, we had that in our last expression. I erased that, but it should be right here. So for any epsilon greater than 0, there is a delta greater than 0 such that if 0 is less than the absolute value of x minus c is less than delta, then, of course all this is true, but what we really care about is then here that the absolute value of 1 over g of x minus 1 over k is going to be less than epsilon. And by that epsilon delta definition, what does that mean? Well, of course, it means what we're trying to prove, and it implies by that definition that the limit as x goes to c of 1 over g of x is going to equal 1 over k. And so we know this now, and how can we prove that quotient property? Well, we're taking the limit as x goes to c of f of x times 1 over g of x. And remember, the limit as x goes to c, we know both these things are given, is the limit as x goes to c of f of x is equal to L. And based on our product property, this is going to equal L times 1 over k. Because again, this limit, we just proved this limit, so we get the limit as x goes to c of f of x over g of x is equal to L over k. And that is how you prove that quotient property. So we're going to take a look at our last property, and that is the product property. In this property is that the limit as x goes to c of f of x to the nth power is equal to L to the n. And this is in the case where the limit as x goes to c of f of x is equal to L, and n is some positive integer. So, 1, 2, 3, 4, 5, 6, all the way up. And so how can we prove this? Well, this proof is actually pretty easy. It uses something called mathematical induction. So if you don't remember what induction is, definitely go over that. Look up some videos or some tutorials on mathematical induction. We'll explain it to the best of our ability, but it is a very good thing to know. So the first thing we're going to do, and this might seem kind of counterintuitive, but you'll see why we're doing it in a quick second. And if you know induction, you'll know why we're doing it. Well, we're going to assume that the limit as x goes to c of f of x to the nth is equal to L to the n. So we're assuming this. And you're like, well, isn't that what you want to prove? Why are you assuming it? And you'll see in just a second. So we're assuming that this statement is true. And what we want to say is that it's true for n, and we want to prove that it's true for n plus 1. So we're assuming it's true for n. How can we prove it true for n plus 1? Well, if this is the limit of f of x to the n, then we're going to try and find the limit of f of x to the n times f of x. And based on our product property that we just proved, we know that this will be L to the n times whatever the limit as x goes to c of f of x is. Well, that's just L. So let's see what we get. So the limit as x approaches c, this is just f of x to the n plus 1. And we get that this is equal to n to the L plus 1. So we've shown that if this statement is true for n, it's true for n plus 1. Well, why have we done that? Well, now we're going to look at a bit of a specific case. So we're going to try and prove this statement true for specifically n equals 2. How can we do that? Well, let's find the limit as x goes to c of f of x times f of x. Well, as we discussed by the product property, this is just L times L. So now we have the limit as x goes to c of f of x, this whole thing squared, is equal to L squared. So we've shown for n equals 2, that this product property is accurate. We've also shown that if we assume it's true for n, then it's true for n plus 1. Well, what does that let us know? It says that if it's true for n equals 2, it's also true for n plus 1, or n equals 3. And then we can say, well, now 3 equals n, so it's true for n plus 1, which is 4. And we can do that all the way up, and that lets us know that for any positive integer, n, when n is a positive integer, the limit as x goes to c of f of x to the n is equal to L to the n.